Okay, so for this video, we're going to talk about the comparison test. We've learned about the geometric series and p-series, about whether they converge or diverge. Now the question is, if you're dealing with something that's not one of those two types of series, how can you figure out if it converges? So let me go to writing mode. So as an example, let's start off with something really easy. We have the p-series, sigma n equals 1 to infinity of 1 over n squared. We know that this converges. But let's change the color. Let's say you're looking at sigma n equals 1 to infinity of 1 over n squared plus 1. We don't know if this converges because it's not a p-series. It's very, very similar to a p-series, but it's not. So this is where the comparison test comes in. Let's start with n squared. We know that n squared is less than n squared plus 1. Now, assuming that the number you're plugging in is greater than or equal to 1, if you take the reciprocal, that relationship changes. So 1 over n squared will therefore be bigger than 1 over n squared plus 1. Now notice that this is the term for this sequence, and this is the term for this sequence. So what we now know is that every term of the sequence on the left, the p-series, is greater than every single term than the sequence on the right. So it should be that this converges. And that is exactly what the comparison test tells us. So what does the comparison test say? Let's write it down. So the comparison test is as follows. So suppose that after some term, after the nth term, suppose that after the nth term, that less than or equal to some sequence an is less than or equal to some other sequence bn. So we're saying that this sequence bn is always bigger, the terms are always bigger than the sequence an. Now, if the series with the bn terms converges, then so does the series with the an terms. And this is basically this idea that if you're adding a bunch of terms from your sequence bn and they converge, and you're also adding terms from some other sequence an and they're all smaller, they should add up to something less. Now it also goes the other way. If oh no, I have to go. Oh, sorry. So there's a second part to this, my bad. Let me type it. So for this other part, it goes the other way. Suppose that after the nth term that that the bn terms are smaller than the an terms. So if the sum of the bn terms diverge, then so does the sum of the an terms. Now this should make sense because the ANs are always larger than the BNs. If the BNs diverge, that means that they're large enough, something happens so that they diverge. Anything bigger than that should also diverge, is the whole idea. So let's do an example. So example, let's determine if the series converge or diverge. So let's look at sigma n equals 1 to infinity of 1 over n cubed plus 3n plus 1. So usually what you're going to try to do is compare it to something that you know converges or diverges. So looking at this, you can see the highest power term is a cubic. So we know that n cubed is definitely less than n cubed plus 3n plus 1 if n is greater than or equal to 1. Which means if we take the reciprocal, the relationship changes. So 1 over n cubed is greater than 1 over n cubed plus 3n plus 1. So what you notice is that I'm going to call this one, the 1 over n cubed, I'm going to call that my an. And it is strictly greater than greater than or equal to my bn. So we now know that our original series converges. Why? Because our series has terms which are smaller than the terms of a sequence which converge. We know that 1 over n cubed converges by p-series. Thus, the comparison test tells us that our series converges as well. Right? All of the 1 over n cubed plus 3n plus 1 terms are smaller than 1 over n cubed. The sum of 1 over n cubed converges, so they must also converge. Let's do another one. Example. We are going to check to see if this sequence converges or diverges. The sum where n equals 2 to infinity of 1 over n. Oh, sorry. The sum of 1 over natural log of n. Okay. So sometimes this can be a little difficult. I want to start by drawing. I'm going to put in a graph. So here's my graph. Here's my x and my y axis. We're looking at 1 over the natural log. We know that natural log has an asymptote at 0, so here's my natural log. And looking at natural log, you actually know right away it's how it compares to n, or this should be natural log x. This is x. So we know that the natural log of x is less than x, which means if you take the reciprocal, it's changed. 1 over the natural log of x is greater than 1 over x. So we should replace x with n, so 1 over natural log n is greater than 1 over n. The 1 over n will be my an, the 1 over natural log n will be my bn. Now what we know is that the series with terms natural log of n are larger than the terms of the harmonic series we know the harmonic series diverges. Thus, the series of natural log n must also diverge by the comparison test. The terms of 1 over natural log n are greater than 1 over n. The sum of 1 over n diverges, so the sum of 1 over natural log n must also diverge.